Emma?
Thank you, Dan. And thank you for coming to my talk. And this is joint work with Michael Schlosser from the University of Vienna. This talk consists of 4 parts. So I will start with an overview of the classical Eulerian and Stirling statistics and several combinatorial structures from the fishbone family. Then I will present the corresponding generating functions and our bijective proofs of the equidistributions. Subsequently, transformations of basic hypergeometric series will be introduced to give analytic proofs of our equidistributions. And finally, our equidistributions in the context of other combinatorial structures, such as permutations and matrices, will be described. And I will finish and the talk with some open questions. So let's get started. So fishbone numbers are defined as the coefficients of this formal power series. This generating function was first derived by Zagier when he counted regular linearized chord diagrams. And an equivalent form of this generating function was later found by Andrews and Jelinek by applying the Rogers-Fine identity. And in this identity, they used this so-called Q-Pochhammer symbol, which I will explain later. And look at this identity. If we look at the left-hand side, actually, it is not clear why the fishbone numbers are positive because the expansion of the inner term alternates in sign. But if we look at the right-hand side, it is easy to find that the coefficients of this term are positive, so are the fishbone numbers. Now you have seen the connection between the fishbone numbers and an identity of basic hypergeometric series. And I will present more of such connections in the later. So why we are interested in fishbone numbers? Because it has led to many interesting results. The list of reference here is certainly not exhaustive. To name a few, the congruences of the fishbone numbers and their generalizations were studied by Gavin, Andrews, Sellers, Bijovi, and his co-authors. And asymptotic formulas were discussed or derived by Zagier, Jelinek, Ringman, Lee, Rogers, Huang, and myself. And the connection between Q series fishbone numbers were discovered by Andrews and Jelinek. And furthermore, a variety of bijections and generating function has been intensively studied by many people, including Buscimelo, Klassen, Dukes, Kitov, Linussen, and Pavinian, and my co-authors, Fu Lin, Yan Zhou, and Mike Namara, Ollie, Elizabeth, and Ramo and Stein Glimson. And our current talk is about the last 3 atoms, Q series, bijections, and generating functions. So here are the combinatorial structures that are counted by the fishbone numbers, including the fishbone matrices, 2 + 2 free pole sets, 2-1 avoiding inversion sequences, and certain pattern avoiding permutations and the regular linearized chord diagrams. Here, any statistic whose distribution over a member of the fishbone family equals the distribution of ascent on ascent sequences is defined as an Eulerian statistics, and I color them in blue. And anyone whose distribution equals the distribution of zeros on ascent sequences is called a Stirling statistic, and they are in color red. This picture shows that any member of the fishbone family with respect to a blue statistic and a red statistic are in bijection with another member of the family with respect to a blue one and the red one. As a result, we choose ascent sequences as a representative of the fishbone family and ascent and rep as a representative of the Euler statistics, and zero max R-min for the Stirling statistics, and they will be defined in the next page. So what is an ascent sequence? It is a sequence of non-negative integers such that S1 equals 0 and Si is at least 0 and less than or equal to the number of ascents prior to Si plus 1. So ascent is a statistic. It counts the number of integers I such that Si is less than Si plus 1. According to this condition, for example, this sequence is not an ascent sequence because the last position should be at most 4. We count the ascents before the last position. How many? There are 1, 2, 3 ascents. So meaning that the last entry is at most 4. So if we replace 5 by 4, it becomes an ascent sequence. And the other statistics are defined as follows. Rep, repeated entries. It counts the number of repeated entries equals the total number of entries minus the number of distinct ones. And maximal entries, it counts the maximal entries. 0 counts the number of zeros in the sequence. R-min is short for right to left minimal. It counts the number of entries, it counts the entries when it is smaller than all the entries to its right. So it's right to left minimal. So for given this ascent sequence, we can count the 1, 2, the ascents 1, 2, 3, 4. So ascent is 4. And 0 is a repeated entry, appears twice. 1 is a repeated entry. 2 is a repeated entry. So rep is 3. R-min is 3. If they are 0, 1, 4. For instance, 0 is smaller to all the entry to its right. And the max is 3. Because the first 3 entries are maximal entries. 0, there are 2 zeros. In fact, among these 5 statistics, the most difficult one to count is rep, because whether an element is a repeated entry or not depends on the entire sequence. So that's why we come up with a new decomposition of ascent sequences to keep track of the particular statistic rep, and let G, T, X, Q, U, Z be the generating function that counts the length, rep, max, ascent, and 0. With this new decomposition we found in 2018 with my co-authors Fu, Lin, Yanzhou, we came up with this multiple variable generating function. And it has it's a sum of finite product, not surprisingly, because if we set X, Q, U, Z to be 1, then we'll return to the generating function of Fishbone numbers derived by Zagier. And the 2 consequences of this theorem will be present next. The first consequence is that the pair 0 and max is symmetric. If we set U and X to be 1, then we immediately get this generating function, and you can see it is nicely symmetric. So this tells us 0 and max is symmetric on ascent sequences. Second one, we need a bijection together with a bijection on ascent sequence that transforms ascent rep 0 max to rep ascent R-min 0. Then with this bijection, we find 2 equivalent forms of the generating function for ascent and 0. And interestingly, the first one was also derived by Jelinek when he used the decomposition of primitive Fishbone matrices. And the second one appears to be new. And after we finished this paper in 2018, 2 remaining questions were left. The first one is that a conjecture. This was supported by numerical experiments saying that ascent rep 0 max is bisymmetric equidistributed. So the ascent rep is a symmetric pair, 0 max is another symmetric pair. Actually, we were very close to this conjecture. if you look at previous page, if this R-min is a max, then this conjecture would be solved already. So we were close but didn't make it. So in terms of generating functions, it means that the multiple variable, the generating function we derived is invariant if we interchange x, u, and q and z at the same time. And so by either way, we were able to prove it. And the second question is that this equivalence we have proved by a purely combinatorial arguments. Can we prove them directly without using any ascent sequence or fishbone matrices? And the second part of this talk will answer these two questions. The first main result is that we construct a bijection on ascent sequences such that a bisymmetric septuple equidistribution holds. And see the statistics, max and R-min is symmetric. And these two new statistics are also symmetric. And it contains two Eulerian statistics, 3 Stirling ones and 2 new ones. And these 2 new ones, I call them assistant statistics. The EM is short for the entry after the last maximal. So given an ascent sequence, all maximal values are colored in blue. So the entry after the last one is 0. For the particular case, when all entries are maximal, we set EM to be 0. And R pose is a maximal M appearing as an M's R-min and also appears at least twice after M minus 1's R-min. So when M doesn't exist or all entries are R-min, then we set R pose to be 0. For example, given this ascent sequence, all the R-mins are colored in blue, and from right to left, the first repeated R-min is 0, so R pose is 0. And for the second example, again, 0, 1, 4 are R-mins, and from right to left, the first repeated R-min is 1, so it equals 1. So I will briefly present our idea how to construct this bijection 5. We take the divide and conquer strategy. That is, we find 2 parallel decompositions of ascent sequences. For each decomposition, we are able to divide a set of all ascent sequences into 5 disjoint subsets, D1 to D5, T1 to T5 respectively. And then we construct a bijection from DI to TI. And the first decomposition actually was inspired by this new statistic, REM, this assistant statistic. And the second one, so that was found in 2018. And 2 years later, we found a parallel decomposition by this new statistic R pose, and phi is constructed by this in this way. So how it goes, we start with the simplest case, that is the bijection from set D1 to T1. And D1 is set of ascent sequences where only one entry is not maximal. And T1 is set of ascent sequences where only one entry is not R-min. And this can be directly defined. And this will form a basis for us to construct construct a file for other more complicated subsets. By complicated, I mean the set of ascent sequences with less maximal entries or less R-min entries. So for instance, I take the set D2 to T2 as an example. It goes like following. We define 2 transformations. The first one transform pairs of IS. I is in between of EM and maximal. S is an ascent sequence to the set of D2. And the second one transform the pairs IS, but I now is between R pose and R-min. S is again just an ascent sequence to the set of T2. Since by induction hypothesis, we always assume that the sequence a set of assigned sequences with more maximal entries and with more Armin entries, the backjection is already known. So this backjection is already known. Also, this backjection respects this bisymmetric equidistribution condition, meaning that here the max S corresponding to the Armin here, they are equal. And this EM equal to this part R poles. So this bijection is known. With this known bijection, as two transformations we constructed, we are able to define the new phi between D2 and T2. The idea is also applied to construct phi for other subsets, but here I will omit the details. So what's the consequence of this bijection? We are able to keep track of the Armin. Now, again, we get a 5 variable generating function. And by the bijection, we know this generating function is symmetric if we interchange Q and V. And our previous generating function is bisymmetric, but that used a combinatorial argument. In the next page, I will show how the transformations of basic hypergeometric series come into play so that we can prove the bisymmetric symmetric property directly. So what are the alpha phi beta basic hypergeometric series? For indeterminates A and Q, this notation you have seen on the first page when I introduced the Rogers Fine identity. It is a product of it equals 1 minus A, 1 times 1 minus AQ, and so on. And given a sequence of indeterminates A1 and AM, then we can define it as a M products of these Q Pochhammer symbols. And alpha phi beta is this basic hypergeometric series. Know that these parameters are chosen so that there are no holes in the segments of the series. So here is the Sayers transformation. It is a terminating transformation of 4, 5, 3 series. It is terminating because of this factor Q to the power of minus N. And in general, for non-terminating basic hypergeometric series, we always consider the series around Q equals 0. But here, in terms of the generating function for the Fishbone family, we always encounter the power series in R, which equals T times X plus U minus XU. T is the size of the sequence or the length, and this is a factor. And we always expand this series around R equals 0. This corresponding to a basic hypergeometric series in base Q around 1. So instead of Q around 0, here is about Q equals 1 in the context of Fishbone structures. So now using this Sayers transformation, we are able to come up with this non-terminating transformation of 4, 5, 3 series. Now with now this theorem will lead to 2 corollaries. And as you can see, here is in base around 1, around R equals 0, but around Q, base Q around 1. And the first corollary is a non-terminating transformation on 3, 5, 2 series. And this will give an analytic proof of the symmetric property of this generating function. So max and Armin is symmetric. And the second corollary is again a 3, 5, 2, a non-terminating transformation of 3, 5, 2 series. And with this, we can prove the bisymmetric property on assigned sequences. That is, XU I interchanged and Q and Z I interchanged at the same time. Then we can come with this it is the same. Now, I will present our equidistributions in the context of other combinatorial structures. So all the equidistributions I have presented before can be translated into the equidistributions of certain pattern avoiding permutations. And proof ingredients contain, we need to use the bijection on a sense sequence we constructed, and a bijection in the paper 2018. Actually, the second one applies the bijection from Varjanovsky's paper. And second one is for the fishbone matrices. We do not have that many equidistributions, but we have some. Again, use this bijection on a sense sequence plus a bijection by Chen Yanzhou in 2019. Then we can come up with this symmetric distribution. Now I will end the talk with some open questions. The first one is, I have shown you the generating functions of ascent rep 0 max, and also the one for ascent rep max and Rmin. Can we find a unified one for all the 5 statistics? We had one, but it is like half a page long, and it involves 2 summation and 2 products. It's not elegant. I would like to know if there's a unified one that can reduce to the already known by the generating function of 4 variables. And the second question is that, do other members of fishbone family also enjoy these symmetric or bisymmetric distributions? For instance, for fishbone matrices, can one find a statistic that is symmetric with the dimension? And the third one is that, can one prove the bisymmetric symmetric distribution in the language of the representation theory? Because for ascent sequences, they are nice. They have connection to Q series, and they have so many symmetric properties, but not array restricted inversion sequences have such property. So how can we characterize it? What kind of restricted inversion sequences have these symmetric properties? What do not have? So that would be also, in my eyes, an interesting question to study. And thank you for your attention. Oh, okay. Sorry, there is a.
Thank you, Emma, for your talk. Let's thank the speaker. And there is time for a few questions. Are there any questions from the audience? Please feel free to unmute yourself as usual to ask the question.
Do you have any feeling regarding your last questions about, is it Hilbert series or something? Do you have any idea of what? Any guess? Could it be your generating function Hilbert series of something or whatever? So that connection representation theory that you asked. So what would you expect?
Because ascent sequences are form a subset of inversion sequences, and inversion sequences are in bijection with permutations. So I don't know, I'm not an expert on representation theory. I just wonder if there are something on the symmetric group, and all our symmetric results can be, here is also true on this subclass of the permutations. So I wonder if there's something beyond this to see these symmetric properties. Yeah.
So this means that these are mesh, avoiding mesh patterns.
Yeah,
so these are patterns of consequent letters, yes?
Yeah, this is just a certain pattern avoiding permutations.
The letters are consequent in this notation, if I understand correctly.
You mean this notation?
Yeah.
this is called a bivehicular. It means some pattern. So let's say it's 312. No, it's less restrictive than 312 pattern avoiding, because if we restrict into 312, then it's Catalan number. It's less restrictive, then it becomes the fishbone numbers. But yeah, I don't know if this answers your question.
Yeah.
There is a question in the chat stating, do you have any continued fraction expansion of the generating function?
Sorry, I can.
If there is a continued fraction expansion,
no,
no,
I don't have. I have a functional equation of generating functions. Then I use kernel method to solve it. So I maybe it has connection to continued fraction expansion, but I don't know.
Any other one last question, perhaps?
So,
okay. Yes, Martin?
How did you come up with your statistics? Did you do a systematic search, or was it?
Sorry, Martin, I cannot hear you clearly. Can you be a little bit louder?
How did you come up with these statistics? Did you do a systematic search, or was it ad hoc?
Because the statistics actually comes from the permutation. If you see this page, you can still see these are all comes from the classical statistics on permutations. So we were curious because we saw ascent sequences, and we know it's a subset of inversion sequences, and also corresponding a subset of permutations. Then we wonder if we put this classical statistic.
Emma, you're on mute. You accidentally put yourself on mute. Sorry.
Okay. Sorry.
No, it's okay. I can hear her.
I didn't mute myself. Can you hear me?
Yes. Now you're unmuted.
Okay. So when did I stop? Where you cannot hear me?
Yes.
Start from when?
I guess from the beginning.
From again. No problem. I repeat again. So why we start these statistics? Because they are well-known classical statistics on inversion sequences and permutations. And we read a paper on ascent sequences, and we know ascent sequences form a subset of inversion sequences. And also this pattern avoiding permutations is a subset of permutations. So we try to in Maple to see if those statistics also have equidistributions on the subset. And to our surprise, they have. Yeah, that was the starting of our research.
Okay, let us thank the speaker one more time for her talk.